Hello, future physicists. Let's start with something super relatable. Have you ever pulled a rubber band and felt it snap back? Or maybe you've compressed a spring and felt it push back. You can feel the force the spring exerts, right? But did you know that this force is actually energy being stored? That's what we call potential energy, and more specifically, spring potential energy. When we stretch or compress a spring, we are storing energy in the spring. This is called elastic potential energy. The amount of energy stored depends on how much the spring is stretched or compressed, and we can calculate it with this formula. The spring force equals negative spring constant times displacement, where F is the spring force in newtons, K is the spring constant in newtons per meter, and X is the displacement from the equilibrium position in meters. So, when you stretch or compress a spring, the force increases in direct proportion to how far it's stretched. It's pretty cool how a simple spring can store energy, isn't it? Now, let's talk about the energy stored in a spring. When you stretch or compress a spring, it stores potential energy. The formula for the potential energy of a spring is the potential energy equals 1/2 times spring constant times displacement squared, where V of x is the potential energy in joules, K is the spring constant, and X is the displacement from the equilibrium position in meters. Notice that the potential energy is proportional to the square of the displacement. This means the farther you stretch or compress the spring, the more energy it stores, and it grows faster as the displacement increases. So, a small stretch or compression leads to a smaller amount of stored energy, but if you stretch it a lot, the potential energy increases quickly. Now, how does the work done by the spring relate to the energy stored inside? Here's the connection. The work done by the spring force is exactly the change in its potential energy. And the work done by the spring when it's stretched or compressed is work equals negative integral of force with respect to displacement. For a spring, this comes out to be work equals 1/2 times spring constant times displacement squared. What does this mean? It's just a fancy way of saying that the work is the area under the force displacement curve. For a spring, this area turns out to be a triangle, and the work done is simply the change in potential energy. Work equals 1/2 times spring constant times displacement squared. So, as you stretch the spring, you're doing work, and this work gets stored as elastic potential energy. Let's move on to something really important: conservation of mechanical energy. In an ideal system where there's no friction or air resistance, the total mechanical energy is conserved. This means that the total energy in the system, which is the sum of kinetic energy and potential energy, stays constant. So, in a spring system where a spring is stretched or compressed, the energy keeps switching between kinetic energy when the spring is moving and potential energy when the spring is stretched or compressed. The total energy remains constant as long as no energy is lost to things like friction. At the maximum compression or maximum extension of the spring's velocity is zero and all the energy is stored as potential energy. At the equilibrium position, when the spring is neither stretched nor compressed, all the energy is kinetic energy as the spring moves freely without being stretched. Let's look at some real-life examples of spring potential energy in action. You may not realize it, but spring potential energy is everywhere around us. Shock absorbers in cars, these use springs to absorb the energy from bumps in the road. When the car hits a bump, the springs compress and store energy. This energy is then released, smoothing out the car's ride. Mechanical watches, these watches use spring mechanisms to store energy. As the spring uncoils, it powers the watch to keep time. Bungee jumping, the bungee cord stores potential energy when it's stretched, and then converts it back to kinetic energy when the jumper is pulled back up. So, spring potential energy is used in things like car suspensions, watches, and even extreme sports like bungee jumping. These examples show us how energy stored in a spring can be used in practical and exciting ways. Let's now solve an example to solidify the concept. Suppose you have a spring with a spring constant of 200 newtons per meter and the spring is compressed by half a meter. What is the potential energy stored in the spring? We use the formula for spring potential energy, V equals 1/2 times spring constant times displacement squared. Now, substitute the values K equals 200 newtons per meter and X equals half a meter. So, we have V equals 1/2 times 200 newtons per meter times 0.5 meters squared. Simplifying, V equals 1/2 times 200 times 0.25, which equals 25 joules of energy stored in the spring. So, the potential energy stored in this spring is 25 joules. Pretty simple once you know the formula. Let's wrap things up. Today, we've learned about spring potential energy, which is the energy stored in a spring when it's either stretched or compressed. We explored the formula V equals 1/2 times spring constant times displacement squared. We also talked about how work is done by the spring force and how the total mechanical energy in a spring system is conserved. Finally, we saw real-life applications of spring potential energy, from shock absorbers in cars to mechanical watches and even bungee cords. I hope this has helped you understand the potential energy of a spring. I'll see you next time with another fascinating physics concept.